Let's see the topic of integration. The calculus deals with various topics like derivatives, integration, etc. Now, in the first year of the syllabus, we have learnt about differentiation, continued with integration, followed as reverse process of differentiation. So sometimes integration is understood as reverse process of differentiation. So let's recap the derivative, what we have learnt in the previous sessions. Say for example, the derivative which we generally denote by d by dx of x squared by 2 is half d by dx of x squared, that is half d by dx of x squared, which is 2x, which on simplification gives x. Therefore, I understand the derivative of the function x squared by 2 is nothing but x. Is how we understand the differentiation of a function as simplified with the respective formulae. Now, what do we understand with integration as reverse process of differentiation? So, differentiation of this function is this. So, integration of this function would be this. That is, if I take integration of this function x is nothing but x squared by 2 is how we reverse process of understanding. Therefore, it comes to the general conclusion that d by dx of f of x, say, is the function g of x, then that implies integration of the function g of x is f of x, is how we understand the relation between derivation and integration. Integration is the reverse process of derivation. That is, d by dx of f of x is g of x implies integration of g of x is f of x. Therefore, d by dx of x squared by 2 is x implies integration of x is x squared by 2. Integration is anti-differentiation. So, integration is anti-differentiation, is how we conclude with the understanding of integration as reverse process of differentiation. So, let's define the antiderivative of the function. That is, if f dash x is some f of x, that implies f is called derivative of capital F, and this f is called antiderivative or primitive of f, is how we understand the antiderivative of the function. For this, f is derivative of capital F and capital F is primitive of small f. Say for example, derivative of sin x is cos x, that implies antiderivative of cos x is sin x, is how we understand derivative of sin x is cos x and antiderivative of cos x is sin x, is how we understand the derivative and the antiderivative connected with the reverse process. antiderivative is also called primitive of the function. Next is indefinite integral. Now the concept of indefinite integral is from where the actual integration topic starts in the syllabus. So what is indefinite integral? As we know that derivative of, say, x square is 2x, then the derivative is written as d by dx is how we write for this. That implies my integration, which is generally denoted by elongated s or summation s, is the symbol for integration. So as I denote the derivative with d by dx, my integration is denoted with integration, that is this of some function f of x dx is how I denote the integration. That is, if I write integral of this is read as integration f of x dx is how I read this. Therefore, when I write the function which is being integrated with respect to x, where f is called the integrand and x is called variable of integration, because this is the variable through which I am going to integrate of integration is how we understand the notation integral f of x dx. Now let's come back to understanding that if I write d by dx of x squared is 2x, then my integral of this is said to be x squared plus c. Now every function is denoted with plus c, which we're going to see in the later session on why the constant of integration needs to be included. Here c is called constant of integration, which we are going to see out there. So therefore, indefinite integral is denoted by integral of f of x dx, read as integration fx dx, where f of x is the function which is being integrated with respect to the variable x, and f is the integrand, x is the variable of integration, is how we understand. Now, as we take the integral of the function f of x dx is taken to be some function with always c which is attached. This is how the formula is taken. But the biggest question here is, why do we need to put plus c for every indefinite integral which is taken into consideration? For indefinite integral, indefinite integration, I have integral f of x dx is f of x plus c, where c is constant of integration. C is called the constant of integration. The reason for inclusion of c is, if you go back to anti-differentiation concept, I have d by dx of x is 1, or x squared by 2 is x. Say d by dx of x squared by 2 we know is x. That implies integration of x is x squared by 2, because these are anti-differentiation. So integration of this is this, because derivative of this is this. Similarly, if I take d by dx of x squared by 2 plus 2, so this also implies that integration on the right side is equal to the anti-differentiation, that is x squared by 2 plus 2. Similarly, if I take d by dx of x squared by 2 minus 3, and let's see what will be its derivative on the right. So this gives me x minus d by dx of minus 3, which is 0, which is also x, which I get here. That implies my integral x dx can also be written as x squared by 2 minus 3. So I get this to be this. Therefore, concluding, I get d by dx of x squared by 2 minus any constant I include here gives me the value as x. Therefore, integral of x dx is x squared by 2 or plus c is what I get. So this makes us understand that irrespective of whatever is the constant, the derivative of a function always has been the same. Therefore, the integration of this will be plus c, which always comes as the constant of integration. There is some constant which is missing in the antiderivative concept, which is included in every definite integral. So plus c is a must in every problem, because derivative of this is this also is this, and of this also is this. In general, of this function is also x. Therefore, integration of f of x dx is f of x plus c. C is the constant of integration. So now that we have understood the integration as the anti-differentiation, let's take a special case to connect differentiation with integration. That is, if I want to find integral of d by dx of this over dx, then clearly I find that since integration and derivative are anti to each other, they get nullified. In general, I say these two get nullified, which gives us f of x plus c. So integral of derivative is f of x plus c, is how we understand integration connected with derivative as nullifying or cancelling each other to give f of x plus c. For example, integral of derivative of this dx will be x squared plus c, because derivative and integration cancel to give the function itself plus c, the constant of integration. Now there are some standard formulae which we must remember in case of integration, just like the standard formulae in derivatives. So for some standard functions, let's see how we can memorize the integration formulae. To start with, integral of x power n is x power n plus 1 by n plus 1 plus c. Now in this case, we assume x as all real numbers, though I do not mention, it is generally assumed that x is set of all real numbers, or x belongs to R. So integral x power n dx is always equals x power n plus 1 by n plus 1 plus c, and of course n is not equal to minus 1, because if n is equal to 1, this becomes minus 1, then the denominator becomes 0 and hence undefined. So for n not equal to minus 1, x power n dx is this plus c. If suppose my n is equal to minus 1, let's see what the formula reduces to. Then this is nothing but written as 1 by x dx, which is log x plus c, is how we understand the concept of integration. Integral a power x dx and of course plus c. The difference is this is exponential and this is general a, for which I get this assumed that a is greater than 0, because for a negative log is not defined. So I take a greater than 0 and a is not equal to 1. So using this we get the formula for e power x and a power x with plus c out here. Now next is integral of sin x, which is minus cos x plus c. Now here we always have, when there's an integration, there is a derivative also equally attached. So whenever I write integral of some function, then I get d of x, which are very much related to each other. So integration and d of x are very much associated, because whenever I write an integration, I write equally d of x here out there. Next, my integral of cos x is sin x plus c. And then next I have integral of tan x which is log mod secant x plus c. And then comes the next formula continued from the session. Next is integral secant square x, which is tan x plus c. And then integral of cosecant square x, which is minus cot x plus c. And then integral secant x tan x, which is secant x plus c. And then I have cosecant x cot x, which is minus cosecant x plus c, is how we have the trigonometric integration formula. And then I have integral 1 by x, which is taken as log x plus c, and integral log x x if this is assumed with base a, integral log x is x into log x minus 1 of dx, is how we get the list of formulae in connected with the standard functions. Now continued, we have integral tan x is log mod secant x and plus c, and integral cot x is log mod cosecant minus cot plus c, and integral tan x is log mod secant x plus tan x plus c. And then I have integral cosecant x is log mod sin x, integral secant x is log mod plus c. And then we have integral 1 by root 1 minus x squared, and of course x is assumed to be outside 1 and minus 1. We don't have the value outside of 1 and minus 1, so x is between 1 and minus 1. So with this I get this as sine inverse x plus c. And integral minus 1 by root 1 minus x squared of dx is cos inverse plus 6. So if I have 1 by root, it is sine inverse, and minus 1 by root this is cos inverse. To be continued with the rest of the formulae in the session. Next, if I want to find integral of 1 by 1 plus x squared dx, then this is tan inverse x plus 6. Or if I want to find integral of minus 1 by 1 plus x squared dx, this is cot inverse x plus c. And then if I want to find integral of 1 by mod x root x squared minus 1 of dx, then this would be secant inverse x plus c. And similarly, if I want to find integral of minus 1 by mod x root x squared minus 1, this is minus cosecant inverse plus 6, assuming x is greater than 0. So this is how we get the values which are between 0 and 1, assuming on the domain to be restricted based on root and mod. Is how we get the formula. Now let's see the integration of some hyperbolic functions. So integration of hyperbolic functions. So we're going to find few of the integration of the hyperbolic functions in this session. Say I have the hyperbolic function sine hx. We know that the hyperbolic functions are with the respective formulae. So integral of sine hx dx is given by minus cos hx plus c, is how we identify. And integral of cos hx dx is minus sine hx plus c. Similarly, if I want to find integral of secant square hx dx, then this is nothing but tan hx plus c. And cosecant h square dx is given by minus cot hx plus c. And then I have integral secant hx tan hx dx is given by minus secant hx plus c. And then integral of cosecant hx cot hx dx is given by minus cosecant hx plus c, is how we proceed with various hyperbolic functions. And similarly, if I want to find integral of 1 by root 1 plus x squared dx is given by sine h inverse x, or this is also log x plus root 1 plus x squared. I can use this or this for finding integral, and of course plus constant of integration. Next, integral of 1 by root x squared minus 1 dx is cos h inverse x plus c, or this is log mod x plus root x squared minus 1 of plus c, is how we have various hyperbolic functions with their respective formulae. Next is the properties of integrals, because to solve an integration problem, the properties help us very much in proceeding with the steps. So let's see each and every property of integral to understand the solving process of integration more better. Say for example, I have two functions f1x, f of x plus or minus g of x dx. So when I'm adding or subtracting the two functions, I get the integration which can be split separately out here. So integration is split accordingly with f of x and g of x. And the second property is, if I have any constant k multiplied to the function, then that constant can come out freely out of the integration. Because the multiplication of the constant does not affect the integration process. So these are the two properties of integration which we take into account when we solve some of the problems. Now continue from the session. If suppose there are n functions and n constants, say for example, I would like to find integration of a1 f1x. Whole of dx, then this is split accordingly with each of the term, because splitting the sum of integration is not restricted only to two functions but to infinite number of functions, here n different functions. So I can split this as a1 f1x plus or minus a2 f2x plus or minus integral an f(x), which can be split as different integrations out here. Now again, the constant which does not affect the integration can be taken out, and I get is how we understand the splitting of the integration for infinitely many functions, is how we understand the property of integration. Now let's see the special cases where if I want to find integral dx, then what is the value of integral dx is the biggest question. Now as we know that integral and derivative get cancelled, therefore integral of dx is always said to be x plus c. Derivative of integral of dx is x plus c. Similarly, if I have integral of 0 dx, then this is how much is the biggest question. So in this case, integral of 0 dx is assumed to be the constant of integration c, is how we understand the concept. Next, if I wanted to find integral of mod x dx, then what would be the value of integral mod x dx? Now that implies mod x is plus or minus x is what we have Substituting for mod x, I get plus or minus x dx. That implies that is equal to plus or minus integral x dx. Plus or minus integral x dx is x squared by 2 plus c. Therefore, integral mod x dx is plus or minus x squared by 2 plus c is what we get as special cases of integration connected with the special cases of the functions. Integral dx is x plus c. Integral 0 dx is c, the constant of integration. Integral mod x dx is plus or minus x squared by 2 plus c. Is how we understand the concept. Let's do some practice problems to understand integration more better. So for example, I have to find integration of x squared minus 2x plus 5x cubed minus 1 of dx. Then this integration, always we need to remember that before we proceed with integration, there are two things which we need to take in mind. One is the standard formulae which we have seen just now, and the properties of integrals which we have considered in the previous session. The standard formulae and the properties of integrals make us get the answer for this problem in a stepwise process. So let's see how we can get the answer for this question using the formulae and the properties. So as we know that integration can be split in plus or minus, I first split each of the terms out here. So this is how I split each of this, and this dx. Now we know that integral of x power n dx is x power n plus 1 by n plus 1 is the formula which we have discussed in the standard formulae. So using this, initially I just split all the constants out because constants are independent of integration in multiplication, so they can be taken out. So this is what we get. And then using the formula here, n is 2 because x squared, n replaced with 2 gives us x power n plus 1 by n plus 1. N plus 1 by n plus 1. And here n is 3, so I get this to be 3 plus 1 by 3 plus 1. And this is integral dx is x, as we know, as a special case. So no dx after integration, because integration is only for dx, but once integration is substituted with formula, there's no dx down. And of course, the constant of integration should not be forgotten, because every indefinite integral when simplified has plus c compulsorily. So this 2 gets cancelled, and therefore integral of x squared minus 2x plus 5x cubed minus 1 of dx is given by x cubed by 3 minus x squared 5x power by 4 minus x plus c. Now rearranging them in order, is what we get as integration of this is this, using the properties and the formulae. Now next, let's see how we can use division process in solving the integration problems. So here I have integral of x power 6 minus 1 by x squared plus 1 dx, which I need to simplify. So x power 6 minus 1 by x squared plus 1 can clearly be divided using the remainder theorem, a equal to bq, the division algorithm a equal to bq plus r. So let's divide the polynomial this with x squared plus 1. Now clearly we know that this, when multiplied with x power 4, gives x power 6 plus x power 4, which on subtraction gives this minus 1. And then this, when multiplied with minus x squared, gives minus x power 4 minus x squared, which on adding gives x squared minus 1. And therefore this on adding gives us 1 times of x squared plus 1, which gives minus 2 as the remainder. Therefore this term can be written as by x squared plus 1. So we get this as minus 2 by 1 plus x squared. When I split this into the mixed fraction, this plus this divided by this is what I get on simplification. That implies integrating on both sides, I get this to be integral of dx, which on splitting gives us integral x power 4 dx minus integral x squared dx plus integral 1 dx, which is dx, minus 2 times integral 1 by 1 plus x squared dx. Splitting the integration and taking all constants out, I get this. Then using the standard formulae, we have two standard formulae, whereas integral x power n by n plus 1 and integral 1 by 1 plus x squared is tan inverse x, which are the two formulae I'm going to use here. So n being 4, n x power 4 is x power 4 plus 1 by 4 plus 1 minus 2 plus 1 by 2 plus 1, and integral dx is x, because we know this as the special case integral dx is x, minus 2 times integral 1 by 1 plus x squared dx is tan inverse x plus c, is what we obtain for integral x power 6 minus 1 by x squared plus 1 of this is how we do using the division process, and then finding the integration becomes easy. Now next is the using expansions. Let's see how sometimes we need to expand and then we get the integration using expansions. Say for example, I have here two of the expansions factors which I'm going to split through expansions. That is, initially I see that I need some expansions here, that is, this is in the form a plus b whole square. So I use the formula a square plus 2ab plus b square is what we get as a square plus 2ab plus b square times x minus 1 dx. Now this x get cancelled and I get this to be integral x square plus 1 by x squared plus 2 times of x minus 1 dx. Now further, this and this are two factors which I'm going to multiply to reduce that into a single term. So this on expansion gives x squared multiplied with x is x cubed minus x squared plus x by x squared minus 1 by x squared plus 2x minus 2 whole of dx. This on further simplification reduces to x cubed minus x squared plus 2x minus 2 minus 1 by x squared dx, and hence I'm going to split the factors, that is integral x cubed dx minus integral x squared dx plus 2 integral x dx minus 2 integral dx integral 1 by x squared dx is what we get when I split the integral with respect to each of the terms. Now integral x cubed is using the formula x power n is n plus 1 by n plus 1. This is x power 4 by 4 minus x cubed by 3 x squared by 2 minus 2x minus integral 1 by x squared I can write as x power minus 2, which is 1 by x squared, and therefore n is minus 2 plus 1, so I get n plus 1 by n plus 1 plus c. Your n is minus 2 in this case if I reduce that into the form. This is minus of minus plus of c is how I understand the integration of this function is this, using the expansion of a plus b whole square multiplied with the factor. The product of two factors on integration, it gives us the answer as x power 4 by 4 minus x cubed by 3 plus x squared minus 2x plus 1 by x plus the constant of integration c. Suppose I have the function which has to be integrated as x squared minus x root x plus 3 plus x power 1 by 3 by of dx. Now this has the fractions with numerator and denominator, where in case of these kind of problems where there's only one term in the denominator, we think of splitting the fractions. For these kind of problems where there's only one term, let's see how I can split the fractions. X squared by x power 5 by 2 minus x root x by this plus 3 by this plus this of dx is what we get. Now this on further simplification gives a power m by a power n is a power m minus n, and therefore this gives us 2 minus 5 by 2, and x root x is x power 1 by 2 by x power 5 by 2, and this gives 3 times x power minus 5 by 2 plus this minus this on this. That is, by using a power m by a power n is a power m minus n as the law of index. Now this, on further simplification, gives 4 minus 5 is minus 1 by 2 minus x power 3 by 2, that is 1 plus 1 by 2, because a power m times a power n is a power m plus n. So 1 plus 1 by 2 is 3 by 2 minus 5 by 2 using this formula. Plus 3 times this plus x power 2 minus 15 of this. Now this, on splitting the fractions, I get x power minus 1 by 2 dx minus x power minus 1 dx on LCM plus 3 times of this dx. Now this, on simplification, gives x power integral x power n dx is x power n plus 1 by n plus 1 plus c. So using this, I get n plus 1 by n plus 1 minus, this is integral 1 by x, which I have, is log x plus c, and therefore integral 1 by x is log x and plus 3 times x power minus 5 by 2 plus 1 by minus 5 by 2 plus 1, and then plus x power minus 13 by 2 plus 1 by minus 13 by 2 plus 1 plus c is what we get when we integrate each of the functions out here. So continued from here, I get this to be x power half by half and minus log x plus 3 times of x power minus 3 by 2 by minus 3 by 2, and this reduces to x power minus 13 plus 2 minus 11 by 2 plus c, which on further simplification gives us this 2 comes to the numerator as 2x power half minus log x, and 3 cancel, is what we get as integration of the given problem. On simplification gives this. So therefore, when we have a single term in the denominator, we think of splitting the fractions and then integrating each of the term using the respective formulae. Is how we do using splitting the fractions. Now let's see some problems based on trigonometric functions. Now basically, when we solve integration of trigonometric functions, we need to understand the concept of trigonometric functions which are learned in the concept of trigonometry. Most of the formulae which are discussed are again revisited when we do integration. Say for example, I take the problem where I want to integrate the function sine square x by 1 plus cos 2x. dx. So let's see how we can integrate this function. So let's recap with some of the trigonometric formulae which I learned in the previous session to do the integration of trigonometric functions. So when I have integral of sine squared x by 1 plus cos 2x, we know that 1 plus cos 2a is 2 cos squared a. Is 2 sine squared a, is how we understand the two concepts of 1 plus cos 2a and 1 minus cos 2a. Now, we have this as sine squared x by 1 plus cos 2a, which is 2 cos squared a. Therefore, 1 plus cos 2x is 2 cos squared x of dx. Now, 2 is a constant. Therefore, I can bring it out, which comes as 1 by 2 of sine squared by cos squared. Now, we know that sin x by cos x is tan x. Using this formula of the sin x by cos x is tan x, I can write this as sin x by cos x whole square of dx, which reduces to tan square x dx is how we get. Now we know that 1 plus tan square theta is secant square theta. That implies I can split tan square x as secant square minus 1. So this reduces to secant square minus 1 of dx using this formula 1 plus tan square is secant square. Now splitting this, we get integral secant square x dx minus integral of dx is what we get. Now we know that integral of secant square x dx is tan x plus c. As we have seen in the standard formula, integral secant square is tan x plus c. So therefore, I get this to be tan x minus x plus c. Therefore, integral of sine squared by 1 plus cos 2x dx is tan x minus x plus c. So this is how the trigonometric functions are integrated using the respective formulae we have in trigonometry. Trigonometric functions connected with integration.